So we've been talking about polynomials for quite some time, and I just want to be very explicit about what a polynomial is and give some examples of polynomials so we can talk about the closure property. So what is a polynomial? An expression consisting of variables and or coefficients that involves only the operations of addition, subtraction, multiplication, and non-negative integer exponents of the variables. So there's a lot of information in here. So you want to make sure that you're using exponents of 0, 1, 2, 3, 4 non-negative integers. Each term is separated by either addition or subtraction. And inside each term, you can have multiplication. It is totally okay to just have a number. We talked about those constants. Constant is considered part of an expression. Each one of these examples are not polynomials. So having division doesn't work. Square root is not an integer exponent. This particular problem has a negative exponent. And again, you've got some division here. None of these are examples. If you take a moment, I want you to look at these warm-up problems and circle the functions that are polynomials. All right. So any polynomials that you can figure out. And there aren't many. So f of x is a polynomial. It's a really basic one. It's a constant, but it's a polynomial. G of x, because you are dividing, is not a polynomial. H of x, square root function, is not a polynomial. This is an exponential problem, so this J of x is not a polynomial. K of x, let's see, 1/2 is fine as a coefficient, x to the 5th, all right. So K of x is fine. And M of x here, while it looks like it might be promising, if you actually take 2 minus 9, you would end up with a negative exponent, which would not then make it a polynomial. All right, we've kind of talked a little bit about polynomials now, so let's talk about closure. And this is going to sound weird, but here's how it works. When an operation is performed with any number or expression in a set, in this case we're going to be talking about polynomials, and the result is in the same set, polynomials, it is said to be closed under that operation. So basic idea here, if I add two polynomials, do I get a polynomial? If I subtract polynomials, do I get a polynomial? If I multiply or divide polynomials, do I always create another polynomial function? And so that's what we're going to figure out. Now, we're going to do two examples here. We're going to do integer and see what integers are closed under, and we're going to do polynomial and see what polynomials are closed under. So to be closed under addition means if I add these two together, I need to create an integer. So off to the side here, I'm going to do 437 plus 25, and I get 462. 462 is an integer, and no matter what you do, if you add integers, you're going to create integers, so this is considered closed. All right. Now, let's do the same thing, but this time we're going to look at a polynomial example. Now, you guys have been doing adding like terms, sorry about that, for a while, so make sure you're only combining like terms. Let's see, 3x here and 2x, and the 7 and the 5 would be combined. So 4x squared plus 5x plus 12. Now this is just one example, but we've added the two polynomials and we've created a polynomial, and that's always going to happen. You guys have done these polynomial problems for a while. You always will create another polynomial. So polynomials are closed under addition. Okay, let's go ahead and take a look at integer subtraction. So 437 minus 25 is going to be 412. And here's the thing. Even if I reverse those and did 25 minus 437, I'd get a negative number, but it's okay to get negative numbers as integers. So that is closed. All right. As long as you add or subtract integers, you are going to create an integer. If we look at polynomial subtraction, I do want to distribute this negative. So 4x squared plus 3x plus 7 minus 2x minus 5. Combine some like terms. So 3x minus 2x, 7 minus 5. I'm just put this off to the side here so I have some room. Let's see, 4x squared plus an x, and then plus 2. We've subtracted polynomials. We created a polynomial. That is closed. No matter what way you subtract polynomials, because you're just subtracting or adding like terms, you're still going to create polynomials. All right. All right. Back to our integer example here. We've got 437 times 25. So let's see, 10,925. That's still an integer. All right. And it's not going to matter which order you multiply. Integers are closed under multiplication, which means if you multiply two integers, you create an integer. Let's see what happens when we do, and I'm going to zoom in a little bit so I can just work on this, polynomial multiplication. So I'm going to take 2x times all three of these terms. So that's going to be 8x cubed. That's going to be plus 6x squared plus 14x. For giggles, I'm going to switch colors, and then I'm going to take 5 times all three of these. So plus 20x squared plus 15x, and then plus 35. There are some like terms to combine here. So 8x cubed plus 26x squared plus 29x plus 35. So when you multiply polynomials, you are always going to create a polynomial. So that is considered closed under multiplication. All right. Now, last step here is going to be to look at our division. So let's see, 437 divided by 25 is 17.48. Now, because we got a decimal here, all right, this did not divide right. I shouldn't say it didn't divide right. It divided fine, but this is not an integer. Okay, integers do not include values that have decimals after them that are not the decimal of 0. So this is open. Now, you can have examples of integers that divide perfectly. So something like 16 divided by 2. Well, that's just 8. So integer divided by integer equaled an integer. Great. But as soon as you have an example of something that doesn't work, and 17.48 is not an integer, the entire set is considered open for that particular property. Let's see what we've got for this problem. We're going to do a little long division. All right, we've done some before, but let's see, we can do a little bit more practice here. So 2x plus 5, and we are going to divide that into 4x squared plus 3x plus 7. All right, so 4x squared divided by 2x is 2x. There's 4x squared. What is that? Plus 10x. I'm going to subtract both of these. So those two terms cancel. That's going to be negative 7x plus 7. Yeah. So let's see. Negative 7x divided by 2 is negative 3.5x. Or just negative 3.5. Sorry about that. Let me take out the x. So let's see. Negative 3.5 times 2. Let me double check that. Yep, that's negative 7. I did it right in my head. And then negative 3.5 times 5 is negative 17.5. Subtract that, and we're going to have then a remainder Whoops, no remainder. Yeah, it is a remainder. I'm just doing the math in my head backwards. So those two terms will cancel. And then this is going to be 24.5. So plus 24.5 divided by 2x plus 5. Okay, so a little long division here. Kind of goofy with the decimal. That's okay, it happens. The bigger problem is that we have a remainder here. And because we have a remainder, this is absolutely not okay. All right, this did not work out nicely. And so because this is not a polynomial term here, whoops, there's my iPad's moving there. Because this doesn't work, this is considered open for division. So yes, we've had problems where we can do the division perfectly and it works out every time, or it works out sometimes, but it doesn't work out every time. So division is considered open for polynomials. All right. So a little practice set at the end here. Use the functions as examples to show that the set of polynomials is closed under addition. So we've got these two polynomials. We've got f of x here, and we have g of x here. All right. And it says that we're supposed to use this to prove that it's closed under addition. So if I take these two polynomials and I add them, I should create a polynomial. So let's do that. Let's see, negative 8x squared plus 12x, let's see, minus 18. This is absolutely a polynomial. All right. So what did I just do? I added two polynomials and created a polynomial. So the set is closed. All right. And if I want to get really specific, so the set is closed for addition. All right. All right, so there's that one. Let's take a look at problem number 2. Use the functions to show that the set is closed under subtraction. All right, we'll do the exact same thing. Negative 8x squared plus 10x minus 15 minus 2x minus 3. So combining like terms, remembering that you're subtracting, so plus 8x and then minus 12. So explain your work, take the exact same thing, but instead of adding and closed for addition, I subtracted two polynomials and created a polynomial. So the set is closed for subtraction. All right. Problem number 3, use the functions to show that the set of polynomials is closed under multiplication. So negative 8x squared plus 10x minus 15 times 2x minus 3. A little distributive property here. So negative 16x cubed plus 20x squared minus 30x. Let's see, plus 24x squared minus 30x plus 45. All right, combine some like terms. Let's see, plus 44x squared minus 60x and then plus 45. Okay, so same exact explanation. I multiplied two polynomials and created a polynomial, so the set is closed for multiplication. Okay, and just to show that, let me go ahead and actually, I'm just going to be a little bit lazy here. Let me copy that, paste it, and just do a little clean up here so I can change it. So let's say I subtracted two polynomials, so the set is closed for subtraction. And then if I paste it again, because why not? It's the same explanation for each one of these, so you don't have to, reinvent the wheel here to make it work. I multiplied two polynomials and created a polynomial, so the set is closed for multiplication. Okay. Use the functions as examples to show the set is not closed under division. Now, this is one of the easiest ones in the world. There is absolutely nothing that says that you have to divide in any particular order. So I actually just make my life really easy and just say, well, what's g of x divided by f of x? Well, g of x is 2x minus 3 over negative 8x squared plus 10x minus 15. I can't take 2x divided by 8x squared. It's just not going to happen. And so that doesn't work. Okay? And so if I look at my explanation, let's see if I paste it. I'm not sure if I can actually do this one. So let's see. I divided two polynomials, and let me slide this over so I give myself a little bit more workspace. And did not create a polynomial. Let's see. So the set is open for addition, not addition, whoops, for division. I forgot to take that word out. Division. And that's going to be true of all polynomials. All polynomials are closed for addition, closed for subtraction, closed for multiplication, and it is a set. It is open for division. Because while I can find a few examples that do work for division, where I create another polynomial by dividing, in general, the set is considered open because you can find an example that doesn't work. All right, so that's the closure property. Let me know if you have any questions or concerns about it, and I will help you out with that.